So then let me introduce Mr. Patrick Stewin. He is security researcher at TU Berlin, and he talks today about placing malware in the Intel AMT chips, which are in all modern Intel-based computers that have been produced in the last 5, 6, or 7 years. And please give a warm round of applause to Mr. Patrick Stewin.
Yeah, welcome to my talk about persistent, stealthy, remote-controlled, dedicated hardware malware. You also see a second name on the title slide, Yuri Bistrov. That means that everything that I will be presenting in the next hour is joint work that I did together with Yuri. Okay, a prominent example for persistent, stealthy malware is a rootkit. And the question is now, why not just deploying a rootkit in user space to attack a computer platform? Well, the point is that countermeasures applied in a more privileged layer, here in the kernel layer, are more powerful, and that enables the defender to reveal rootkits that are applied in the user space. But it didn't take so long that the malware developers also recognized that the kernel space is more powerful, and that's why malware developers developed malware for the kernel space. And this resulted that the countermeasures moved to the hypervisor layer or to the virtual machine monitor layer. That's a layer that can deprivilege the operating system kernel to be able to host several operating systems in parallel on the same computer hardware. But guess what happens next? Also, the rootkits move to the hypervisor layer. Prominent example is Bluepill or Subvert. And we can continue this arms race to the system management mode. It's the most privileged host processor mode on Intel platforms until we reach platform peripherals. And platform peripherals are the focus of our malware that I will be presenting in the next minute. When we talk about peripherals, we mean network interface cards, for example, or the video card, or special microcontrollers that are somewhere in the chipset. And the point of peripherals is that they actually provide an own execution environment. That means an own processor, own RAM, and they can access the runtime memory of the host via a mechanism called direct memory access. And the good point for the attacker is that these environments are unconsidered by antivirus software, for example. And at this point, the anti-malware community has a problem because there is no more privileged layer that can be exploited for countermeasures. And that's why we did our research with peripherals. Okay, this is an overview of the rest of my talk. In the first part, I will present you a DMA-based keystroke logger that we call Dagger in short. In the second part of my talk, I will present you an out-of-band network channel that is somehow isolated from the host system, and we exploit that channel to stealthily exfiltrate captured keystroke codes to an external platform. And in the third part, we also did some research with the covert network channel, because the out-of-band network channel is only stealthily for the host system, but other systems that are monitoring the network can, of course, reveal the network packets sent by our keystroke logger. Okay, now let's come to Dagger, our DMA-based keystroke logger. What is Dagger? Some days ago, I was asked if Dagger has something to do with the Dagger complex. The Dagger complex is a base of the US intelligence organizations that is operated on behalf of the NSA here in Germany, in Darmstadt, to be more precise. And of course, one could think that keystroke logger is somehow related to surveillance attacks. But be assured, the dagger that I will be presenting here is not related to the dagger complex. So our dagger is actually part of an academic research project. It's written in C and Arc4 assembly. I will later explain why Arc4 assembly. And it's actually not only a keystroke logger anymore. We updated Dagger, and I will later explain the updates. Of course, Dagger can access the host runtime memory via DMA reads and writes. It uses the isolated network channel, and we can attack 32-bit and 64-bit operating systems. So here on this slide, you see a more detailed view of our attack environment. And what you see here is actually an Intel-based Q35 chipset. You see the memory controller hub, also known as North Bridge, and the input-output controller hub, also known as South Bridge. And our device that we exploit to implement Dagger is the so-called manageability engine, also known as management engine. And this device is incorporated into the memory controller hub. It consists of an Arc4 processor. That's why we implemented some parts of Dagger using Arc4 assembly. And that processor is a 32-bit RISC processor. It is not x86 compatible. The management engine also consists of some static RAM, some ROM for the boot up code, and of course a DMA engine. So for runtime data, for runtime code and data, the management engine uses some isolated part of the normal DRAM chip, and the chipset enforces that only the management engine can access that part of the normal DRAM. That means the operating system, your Windows, your Linux, cannot access that part of the memory. So then, here on the South Bridge, we have the out-of-band channel that we will later exploit to exfiltrate our keystroke codes. And the management engine is used to execute some firmware. The firmware is based on the ThreadX real-time operating system. And firmware that can be executed on the management engine is, for example, Intel's active management technology. Here on the right-hand side, you see an administrator tool that uses the Intel active management technology to remotely boot into the BIOS of the target system. And as you can see here, the actual operating system and the network stack of the operating system is not up and running if you boot into the BIOS. That means that this administration tool is quite powerful. Intel's active management technology is mainly deployed on business computers. On other platforms, you find other firmware such as Intel's identity protection technology or anti-theft. Okay, here some more background information. First of all, you should know that there are actually two generations of the management engine. The first generation is based on the Arctangent A4 processor, or in short Arc4, and the second generation is based on the Arc-Compat architecture. We use the first generation for Dagger, but there's also some research related to the second generation available. You should have a look at Igor Skochinski's slides to his talk Rootkit in Your Laptop, where he published the first results regarding the second generation. And there's also another relatively new project that is related to the management engine, and that project wants to deploy free software on the management engine. Their goal is to actually deploy an ME replacement compatible with the core boot firmware. If you are more interested in that project, then you can visit the webpage, the project webpage, the Intel vPro webpage. Or if you want to talk with these guys face to face, just visit the assembly here at the Congress. Okay. Another point is, or another important point is that the management engine had actually a predecessor, and maybe you remember a Super Nintendo video game from the beginning of the 90s. There's a screenshot on the right-hand side. The game is called Starving, and it had amazing computer graphics for that time. And to implement such kind of graphics, the cartridge that you had to plug into your Super Nintendo had an additional chip that was called the Mario chip. And that Mario chip was later renamed to Super FX. And again, later it was renamed to ARC because it was a predecessor of the ARC technology, what we have nowadays in our Intel platforms. The main character of the Starving game was called Star Fox, and Star Fox used the ARC technology to, of course, rescue the universe, and this clearly demonstrates, or also demonstrates, how powerful the ARC technology actually is. Do we know what happened to Star Fox? I don't know, and neither does Intel, and that's why Intel is completely alone responsible for making the ME environment bulletproof, and they do so by applying a bunch of security mechanisms. For example, they use signed firmware images, and they also apply a measured launch mechanism. That means before the firmware gets executed, a hash value is derived, and that hash value is compared with a well-known reference value. And for the login or remote login capabilities, there are also some access control mechanisms in place. So the question is now, how do we infiltrate the target platform with our dagger? Yeah, we just reuse a known exploit that was discovered by the Invisible Things Lab guys. And if you are also interested in this kind of research, you should check their slides from the Black Hat 2009 conference, I think, because it's a very good starting point. Okay, back to Dagger. Our actual target is the keyboard buffer because we want to capture keystroke codes. And the operating system loads a driver for a keyboard, and in that driver you can find the keyboard buffer. So now let's dig into the kernel memory to find the keyboard buffer. We implemented two search strategies, one for Linux targets and the other one for Windows targets. Here you see the strategy for our Linux targets. What we try to do is we try to find two memory structures. The first one is called USB request block, and the other one is called USB device. And we check if a pointer is aligned to 0x400, and if another field called transfer DMA is aligned to 0x20. And the transfer DMA field actually represents the keyboard buffer, or the physical address of the keyboard buffer. And if both conditions are true, we follow the pointer to the USB device structure to check the product string, because you have more than just one USB device plugged to your computer. And if the product string contains the substrings USB and keyboard, then we know that we found the correct structure for the USB keyboard. The last final check is that we look into the keyboard buffer if there's any garbage. Okay, to be able to follow the pointer, you have to know that the attacker that uses a DMA engine works with physical memory addresses, but the operating system actually works with virtual memory addresses, and you have to find a way to map the virtual memory addresses to physical ones. Under Linux, that is actually quite simple. You have to subtract a constant offset. For 32-bit Linux systems, it's 0xC000 and so on. And for 64-bit Linux operating systems, you can just look up the offsets in the documentation. The mm.txt file consists of a table that is visualized on the right-hand side, and then you can just pick the correct offset that you have to subtract to follow your pointer. Okay, that was the strategy for Linux. Now let's come to Windows. For Windows, everything gets more complicated. First of all, because of we haven't had any access to the source code, of course, and we had to reverse engineer a lot of things using IDA Pro, the Windows debugger, and also debug symbols provided by Microsoft. And another point is that if you want to follow pointers, you cannot just subtract offsets under Windows. You have to work with the page tables that are also used by the operating system. So that means we had to find the page tables in the runtime memory of the operating system. And we also had to implement a page table traverse algorithm in Dagger. This is what we did. And still, we had to find the keyboard buffer. And after hours and hours using IDA and co, we came up with the following search path. We figured out that a good starting point is a so-called KI initial PCR structure. KI means kernel image, PCR means processor control region. And that structure led us to another structure called debugger data block. And that led us to the next structure called object manager namespace directory, and that namespace directory contains a object directory driver, and that includes the keyboard human input device driver. That means the device driver for the USB keyboard. That in turn contains a device object, and the device object contains a device extension, and the device extension finally contains the keystroke code buffer. By the way, the figure here is simplified. And one point is still missing on the slide. So far, we don't know how to find the starting point, the KI initial PCR structure. This is explained on this slide. We analyzed the boot process, the Windows boot up process, and we figured out that the winload executable calls a function, the load all modules function, and that function allocates a memory buffer for two images, for the hardware abstraction layer image and the kernel image. But the function also applies some address randomization. That means the function determines which image gets loaded first. And in a second step, it also determines the target address of the images. That means, or the function uses a 5-bit randomization seed, and 5-bit means 32 target addresses per load order. And that finally means for us to find the KI initial PCR structure that is part of the kernel image, we had to scan 64 addresses, and this is what we actually do with Dagger. We scan 64 addresses and apply a signature scan to be sure that we found the KI initial PCR structure to find the KI initial PCR structure. Okay, this was Windows. Now let's come back to our attack environment. If we really want to implement that stuff, we have to control certain ME features. First of all, we want to read from the runtime memory. That means we need to know how to use the DMA engine to read from the runtime memory. This was actually quite simple due to previous work. We just had to change 2 bits. But we also want to use the out-of-band feature that is incorporated in the South Bridge to exfiltrate captured keystroke codes. And for doing so, we had to change more than 2 bits. We had to do some more reverse engineering. So this brings me to the second part, the out-of-band network channel. We know that the AMT firmware runs a web server for the administrator to remotely log in to the platform to do some administration stuff. And we know that then the administrator sends a request that the web server will send a reply. And the code that is responsible for sending the reply is actually the code that we want to isolate because we want to exploit it. And the best thing to do so is using a developer board, as shown here, for example, on the left-hand side, because you can turn it around and you will find a nice interface where you can connect debugging hardware to do some programming with the manageability engine. Unfortunately, if you don't work for Intel or for one of Intel's business partners, you don't have any access to such tools. And that's why we had to develop our own research tools. And for Linux, we ported the exploit to a character device driver. This just because, it's more comfortable if you want to use well-known command line tools such as XXD, for example. We can use XXD to access the AMT runtime memory. Another tool is our AMT memory monitor that you can also use to look into the AMT runtime memory, but it also highlights changes in the runtime memory that you won't see if you just use XXD, for example. So, but the most important tool is our AMT breakpoint helper tool. That's a tool that dumps the whole AMT runtime memory on the fly, disassembles it on the fly, represents the disassembly to the user, and the user can choose a location to set a breakpoint. And this tool is actually the tool we use to isolate the code for sending network packets. And we started to send replies to the AMT web server, but then we figured out that it just happened too much, and this was actually a bad strategy. But more or less by chance, we figured out that when we plug in the network cable into the network card, AMT sends exactly one network packet, a DHCP packet, and this is what we eventually exploited to find the network code. We set a breakpoint, then we plugged in the cable, we checked if the breakpoint was triggered. If not, we set a new breakpoint, plugged in the cable again, and so on and so on. And finally, we were able to isolate the code that you see here on the left-hand side. This is a code that you need to send a network packet. On the right-hand side, you see the AMT ring buffer that is used for the outgoing network packets. And with that knowledge, you can prepare a network packet, copy it into the ring buffer, and then trigger the code on the right-hand side, and then your packet is sent to an external platform. And this is what I would like to demonstrate with a demo video. What you see here is the target platform on the left-hand side and the external attacker platform on the right-hand side. We attack a 64-bit system here. Just to show you where it are really two different machines. Both platforms run Wireshark. The attacker platform also runs the AMT web interface. This is just to demonstrate that the AMT firmware is still up and running, even if it's infiltrated with Dagger. And on the button on the right-hand side, just a keystroke code mapping application. Okay. So at first, I demonstrate that the firmware is up and running. I ask for the processor information. It's of course an Intel processor and an Intel platform. So then I infiltrate Dagger on the target platform with some 0-day. And if Dagger has found the key mode buffer, it sends an initial packet to the attacker. This is what you see in the Wireshark instance on the right-hand side, because the Wireshark instance on the left-hand side is unable to see that packet. So let's check the firmware. It's also working. So and now I try to exfiltrate some keystroke codes. You see that on the right-hand side, we got some packets with keystroke codes. This is the enter keystroke code, and here is a key release code. Wait. So now I'm entering a sudo command. And as you can see on the right-hand side, the captured keystroke codes are translated into my standard password, that is secret 100. So that is what I actually wanted to show you. Okay, but this was or is not enough. We updated Dagger a bit because we thought if you can use the out-of-band channel to exfiltrate information, you could also use that channel to update Dagger's attack behavior. And we did it with the following configuration. We know that the MT firmware has several threads. One thread is for Dagger. And in that thread, we have still some space for new attack code. And another thread, AMT thread, is responsible for incoming network packets. And this is a thread that we want to hook. And the hook is actually responsible for analyzing incoming network packets for new attack code. And if new attack code is identified, the hook extracts the new attack code and copies it to Dagger. And if the last packet with new attack code is received, a flag is set. If Dagger sees that the flag is set, it jumps to the new attack code, and afterwards it returns to the monitoring mode. Here in our example, it's a privilege escalation attack that we uploaded to Dagger. But the question is now how to find the code that is responsible for handling incoming network packets. So far, we only know the code that is responsible for outgoing network packets. And to do so, we developed a new research tool that is a bit more complicated, but it has much more features. It's a Windows tool. You can set conditional breakpoints, for example. You can also dump the register content and the memory. You can emulate some firmware parts, AMT firmware parts. But the most important feature of our new tool is the tracelog feature. So we are able to record tracelogs. We can record the instructions that are called, including the relevant register content. And this tool actually revealed us the code that is responsible for incoming network packets. This is what you see here, or what you exactly see here is a memcopy call. And the registers R0, R1, R2 contain the parameters for the memcopy call. That means the destination and the source address and the number of bytes to be copied. This is our main hook of our trace tool. It's not important at the moment. And here you can see that the memcopy function copies byte per byte. And the bytes that are copied here are is the MAC address of the destination platform. And what we do now is we just place our hook just before the incoming packet is copied to the actual AMT environment. So now you know that we found the code to examine incoming packets, but you don't know how we realize the privilege escalation attack. The first thing we do is we check the kernel version. If we know the kernel version, then we can derive certain addresses and offsets and size of structures. And what we want to do is we want to find the init task structure, because the init task is the first task that is executed on a Linux system, and this task runs with root privileges. And the structure also contains a task list of all tasks executed on the system, and we use the task list to find the target task where we want to have more privileges. And what we actually do is we copy the root privileges from the init task structure to our target task structure. And this is what we implemented in C. The resulting binary is called DMA, proof of concept remote privilege escalation.arg4.elf. And we send this elf binary via a tool called hping to the AMT environment. We just use hping3 for, to keep things simple. The tool is able to send almost arbitrary TCP IP packets to network hosts. So, okay, now you know that we can also control incoming network packets, and we can also implement a privilege escalation attack. It's time for the next demo, right? Here again, you see the target platform on the right-hand side, left-hand side, and the external attacker platform on the left-hand side. Both platforms run Wireshark again. The target platform is already infiltrated. We also run the AMT web interface to convince you that the firmware is still up and running. We also run the keystroke code mapping command line tool. And we also run a SSH command to remotely log into the target platform. So, okay, now to show you that Dagger is already up and running, I use an editor to type Dagger is running. So, no big deal. So then I log into the target platform using my standard password, secret100. So now on the target platform, let's check if it's really the target platform, and it is. I check who am I. As you can see, I'm Patrick X, but that's not enough. That's why I check at first if I can execute privileged commands. I obviously cannot because I'm not root, but I would like to be root. That's why I send the privilege escalation attack to the target platform. Then I can check again, who am I? Now I'm root. And now I should be able to execute privileged commands. Yeah, it also works. I think there should also be a last check if the firmware is up and running. Yeah, it is. Okay. So now you saw our out-of-band network channel features, but you also saw that external platforms can also see all the traffic that is generated by Dagger. And that's why we also did some research related to a covert network channel. And the covert network channel that we implemented is based on a so-called jitterbug. We got the idea from an academic paper called Keywords and Covert Channels. And the authors of that paper used an additional device, but we wanted to avoid an additional device, and that's why we implemented the jitterbug using also Intel AMT and the Intel AMT environment. And we use the following setup. We have the Intel AMT machine on the left-hand side. On the right-hand side is the administrator platform. And in between, somewhere in the network, is the attacker platform. And the jitterbug works as follows. Information are encoded by slightly delaying outgoing network packets, and the attacker can measure the inter-arrival times of the network packets to decode the leaked information. So that means that we deployed a jitterbug sender in the AMT environment to slightly delay network packets, and the attacker can decode the network packet, the inter-arrival times to get the leaked information. Obviously, the bandwidth of the network channel decreases, but it's still enough to leak passwords. And another advantage is that it doesn't matter if the outgoing network traffic is encrypted or not, because we just use the packets. Okay. And in our setup, we wait until the administrator initiates a new administration session with the target platform, and if the administrator did so, we can exfiltrate our password that we captured with Dagger. Okay, to do so, we also require some features of the manageability engine. The first one is we need to control outgoing network packets. This is what we already did, so no big deal. But another point is that we also need, we need to measure time to be able to delay outgoing network packets. And we found a timer that is related to AMT using our tracelog tool. And we figured out that we can access a timer at a special register at 0x8011. And this timer has a resolution of approximately 996,500 Hertz. And this is good enough to slightly delay our network packets. And then a third point is that we have to know which traffic we actually can delay, because the delays must look like random noise to all the other monitors present in the network. Before I demonstrate this in my last video, just a short overview of the execution stages of the jitterbug-based Dagger. In the first phase, we find the keyboard buffer. This takes approximately 100 milliseconds. And in the second phase, we wait for user input. We wait for a login name, and afterwards we capture the password. And in the third phase, we wait that the administrator triggers a session to be able to leak the password to the jitterbug receiver. Okay, demo video 3. Here you see the attacker platform. And we start the jitterbug receiver. We chose a network adapter. And we use a pattern to define rotating timing window. This is just to introduce more randomness. There's also a terminal with some statistics. There you see the decoded bit and the distribution within the window, and a frame start sequence to synchronize sender and receiver. So now we start a administrator session, and you can see that the receiver receives something, but it's actually crap because we haven't captured a password so far. So now we are on the target platform. We reuse the exploit that we also used before. So you see nothing because we want to be stealthy. To convince you that we really infiltrated the platform, you can start the driver again, and you see that the keystroke logger is removed. So now we infiltrate the platform again, and we found the keyboard buffer. And now we wait for user input. This is the submission system of the 44Con conference where I gave this talk the first time. By the way, we did not change the password. So you can check if the password still works in a few seconds. So the password is captured, and now the administrator initiates a new session. And now you can see that a password, slowly but it comes, is revealed. It takes some time. As I told you before, the bandwidth of the jitterbug-based channel isn't that high. So now we got the complete password. And fortunately, there are also other administrator tools that enable us to exfiltrate the password a bit faster. We just have to remotely log in using the tool, and then we already got the password. So now let's check if the password is the correct one. And of course it is. So I restarted the video, sorry. Yeah. Okay. So some final remarks. If we talk about attacks, we also have to talk about countermeasures. And a countermeasure that is proposed quite often when talking about DMA attacks is an input-output memory management unit. Intel also implemented a input-output memory management unit. Intel calls the technology Intel VTD, virtualization technology for directed I/O. But this technology also has some issues. It was demonstrated that the I/O MMU can be tricked, amongst other things, also with a DMA attack. And there are other issues. For example, the Windows operating system doesn't include a driver for the I/O MMU. There are also some academic countermeasures, but I actually wanted to point you to Peter Stuge talk that he gave 2 days ago, and he proposes to harden the hardware and to choose a good BIOS. And of course, Peter proposes to use Core Boot as a good BIOS. You should definitely have a look at his slides or at his talk. And now I would like to shortly conclude. This figure here represents our conclusion, because if you want to implement a keystroke logger like Dagger, you have to reach certain milestones. And what you see here is the importance estimated by Yuri and me of the milestones. The importance is not related to the effort we had to put into reaching the milestone. Of course, the most important milestone is the infiltration. Here we were lucky we could reuse an exploit that was provided by the ITL guys. Then we had to find some valuable information in the host runtime memory. In our case, it was a keyboard buffer, but you could also search for other valuable data, such as cryptographic keys, online banking credentials, or I don't know, the Skype session key. And of course, if you found valuable data, you also want to be able to exfiltrate that data to an external platform. That's why we say network access is also quite important. And in the case of our jitterbug-based covert network channel. We also need to figure out how we can reliably measure time. And this is what you have to do if you want to implement persistent, stealthily, remote-controlled, dedicated hardware malware. That's it from my side.
Yes, thank you very much, Patrick. If you leave during the Q&A session, please do so quietly. And if you leave, please take with you all your trash and all your other belongings. So we will have time for a few questions. Are there questions from the internet?
Yes, I have one. So on notebooks, you can disable this Intel AMT. And some BIOSes say that you can disable it permanently. But how can I verify that?
Unfortunately, you can't. So on our board, we also tried to disable AMT via BIOS functions. And we did so, and then we used our AMT memory monitor to check if it's really turned off, but it wasn't. It was still working.
I think Peter Sugo mentioned at his talk that he completely wiped BIOS, overwriting it with zeros, and still it started sending some stuff after turning on.
The good BIOS code.
So the follow-up on that one, can you do that somehow by measuring power consumption?
We actually tried it, but this is a kind of anomaly detection, and you can't be sure what the user will be doing and what the users will be doing with his computer, and it's quite difficult to determine what is correct behavior and what is the wrong behavior and the resulting power consumption. I propose a countermeasure where I measure the memory accesses using certain performance counters. Maybe that is a correct approach.
Okay, we have a question from microphone number 8.
But at the moment, you still need to execute the exploit locally on the attacked system. Have you tried to find remote exploits into the management engine?
We did not try so far, but of course that would be much nicer to have a remote exploit. And as I said, Intel AMT runs a web server, so most probably you will, or you can find a vulnerability, but we didn't so far.
Okay, thanks.
Yeah.
Okay, one question from microphone number 2.
Yeah, 2 questions actually. First of all, well, what's really the prevalence of those devices? Is it only on servers? Is it on desktops? And the second one, does it actually do anything useful? It seems like a huge attack surface, so you really want to remove it, or does it actually do something you would want to?
I think for companies where you have a bunch of computer platforms that can crash, it's actually a useful tool, this AMT, because the administrator can remotely reinstall the operating system, for example. What was the first question?
Is it only on servers, or is it on desktops? Or?
On servers, you actually have similar solutions. This is for desktop. AMT is for desktop and laptop systems. On servers, you have something like the baseboard management controller or stuff like that.
Okay. Yeah. Thanks.
You're welcome.
Okay, next question from microphone number 2.
Yeah, maybe I was missing it, but I'm kind of not seeing like any kind of persistence there. So could you again like maybe clarify what exactly you exploit locally, what you exploit remotely, which is like nothing, I think, and what changes to the systems do you actually do to after it's switched off, plugged into another network, so that it's still there?
Okay, yeah, I forgot to mention how we get the persistency. Okay, AMT is so powerful that you can turn off the platform, or you can put the platform in standby mode and AMT is still up and running, even if you power off the platform. It's only required that the platform is plugged into a power source. And if we infiltrate the target platform and we shut down the system, as usual, AMT or our Dagger is still up and running together with AMT. If you turn on the platform again, also Dagger is up and running. We tested it with a platform encryption mechanism with a Linux system. We infiltrated the platform during runtime, then we turned off the platform, turned it on again. We had to type in the hard disk encryption password and we got it.
So completely removing the power plug or having a completely dead battery will actually remove it?
You have to remove the power plug and the battery.
Okay.
So another question from number 2.
Yeah, I actually want to know if you experienced any difference between host-based provisioning management engines and don't know the other name right now. So the one is host-based provisioning, and I think the other one is something like enterprise provisioned, which overrides the config all the time when a management server is contacted. So do you experience any difference in your expectations?
I don't really got your question or your point. Sorry.
To use Intel AMT, you have to provision the chip. By default, it's enabled but not used, and you have to provision it to enable it.
Yeah.
There are two methods in the actual version right now. Those host-based provisioned, which you do on the host, on the operating system.
Yeah.
And the other is enterprise-based. So you, for example, while the system boots, you plug in a USB stick, and the system gets provisioned and configured and contacts and server, for example, and uses a certificate to do the whole configuration. It overrides all the time. It contacts the enterprise server, for example. On your exploit, do you what method do you use to provision these chips, the management engine?
I don't have any experience with the provisions, but I know that certain systems are delivered to the customer that are already somehow provisioned because they are already asking for a provisioning server at least. So that means they are at least configured to ask for the provisioning server. I don't know if this is useful for any exploits so far.
Okay, one question from microphone number 3.
Yeah, I can mention that it's actually for remote deployment. That's one of the selling points, that the manufacturer can ship the laptop directly to a user, and the company can then push their software. But I had a question. This has been in laptops since 2011. Do you know how many laptops have been shipped?
What?
Do you know how many laptops have been shipped with this lovely feature?
I think all business laptops.
Yeah.
But I don't know if you can ask a manufacturer to leave it out. I don't know.
Okay, one more question from microphone number 2.
Especially on laptops, the keyboard is usually connected using PS2.
Yeah.
Do you support that too?
The Windows version is also able to find the driver object for the PS2 keyboard. Under Linux, we didn't implement it, but at the end of the day, it doesn't matter which keyboard buffer you have to find, right?
Yeah, true. Thanks.
Okay, then give again a warm round of applause to Mr. Stewart. And please, when you leave, take all your trash with you. We don't like collecting your trash, and we'll be back for the next talk later.